Hi everyone, how are you all doing? Hopefully you're doing good, had a nice weekend, and ready to work here in chapter 8. So our game plan for the first half of lecture today is to finish up chapter 8. So what we have left to do for that is two reactions. They're both going to be bromination reactions. So the first one we're going to talk about is the free radical addition of HBr to alkenes, which will be different than the HBr plus alkene reaction we learned in chapter 6. And then the second reaction that we're going to learn about is something called allylic bromination. And so hopefully you're starting to get a sense for the various different ways we have to make alkyl halides or to add bromines to our various starting materials, alkene, alkyne, and now alkane. And so at the end of this chapter, we'll go ahead and compare all the various reactions that we have for making alkyl halides and the like. Okay, so the first reaction that I mentioned that we're going to cover today is called free radical addition of HBr. So free radical addition of HBr to an alkene. Okay, so what I want to do for a second is just recall a reaction from chapter 6. Okay, so recall from chapter 6. All right, so we learned this reaction where we took an alkene and we reacted with HX, we'll use HBr here, and we generated the Markovnikov halide. Okay, so this was Markovnikov addition. Okay, so why was this Markovnikov addition? So what intermediate did we go through that dictated the regioselectivity of this reaction? So remember that we would go through a carbocation, and it was the stability of that carbocation that was generated that dictated the outcome of the product, or the outcome of the reaction to form the major product. Okay, so what is the reaction that we're going to be learning today? Okay, so here is the reaction we're considering. Okay, so here's the free radical addition. And we're going to see we just very slightly change the reagents and conditions to basically change the outcome of the reaction. So we're going to take our alkene and we're still going to react it with HBr, but we're going to add something into the mix. Okay, so we're going to react it in the presence of this molecule, which I'll give you the name in a second. And then we need either heat or light again. Okay, so let's think about what we know about free radical reactions. So the first one is that we generally need some sort of molecule that can initiate the reaction. So for, free radical addition to alkanes, or free radical halogenation, we had either Br2 or Cl2, and we could homolytically cleave those bonds. In this case, that's the role of that molecule that has the two oxygens. Okay, so these types of molecules that have an oxygen-oxygen bond are called peroxides, right? We've seen H2O2 before, which is hydrogen peroxide. So this molecule is another peroxide, and actually that's the role of this reagent in this reaction, is that oxygen-oxygen single bond has a very low BDE, which tells you that it's a very weak bond, and that allows us to shuttle those molecules into a free radical reaction, or reagents into a free radical reaction, by adding in this free radical initiator. Okay, and I'll tell you more about what that thing is called, and I'll give you the actual BDE here in just a second. Okay, so what I want to do next is draw the products of this reaction. Okay, so the products that we form end up being addition of Br to the less substituted side. So we still added HBr across the carbon-carbon double bond, but let's go ahead and count our carbons in the starting material so we can see in the products where we added those halogens. So notice that we added the halide at position 3, which was the less substituted side of our alkene. And notice at carbon 2, we added an H. So we still added HBr across the carbon-carbon double bond, but now this would be an example of an anti-Markovnikov addition. Okay, so this is a regioselective reaction for anti-Markovnikov product. And that's because we're ending up adding the halogen to the less substituted side and the hydrogen to the more substituted side. Okay, so let's make a note of our regioselectivity over here. Okay, so this is a regioselective reaction RxN, and it's regioselective for anti-Marx product. Okay, and we can see that because Br on less substituted carbon and H on more substituted carbon. Okay, so how is it that by just adding this free radical initiator into the reaction, how is it that we can alter the regioselectivity? As compared to the reaction we learned in chapter 6 that we talked about at the beginning of this section. Okay, so in order to understand this, we're going to have to consider the mechanism. Okay, so before we jump into the mechanism, let's go ahead and look at that free radical initiator that I was telling you about. Okay, so this molecule here is called ditert-butyl for the two tert-butyl groups peroxide. And we could abbreviate that as DTB, oops, make that capital, DTBP, ditert-butyl peroxide. Okay, and why we're going to use that is because the BDE of the oxygen-oxygen single bond is 36 kcals per mole. Okay, so think back to the bromine-bromine or the chlorine-chlorine bond, BDE. That was like in the 40 to 50 range. So this is even, a more significantly weak bond, meaning that the oxygen radicals that are formed are even more stable than in the case of bromine or chlorine. Okay, and so the role of this ditert-butyl peroxide is to initiate the free radical reaction. And so what we're going to look at next is, well, once we've made this oxygen radical in the initiation step, how is that going to shuttle this alkene into this anti-Markovnikov reaction? So let's go ahead and look at the mechanism. We'll look at this example molecule that we have here for our mechanism. Okay, so this is going to be a free radical chain mechanism. Okay, so what are the three general steps of a free radical chain mechanism? So the first step is initiation. Okay, and in this case, we actually have two initiation steps. Okay, so remember, initiation is where we're going to generate free radicals from where we didn't already have free radicals. And so there's actually two initiation steps in this one, so we'll just label them as A and B. So the first one is going to be where we've taken our ditert-butyl peroxide and we've done the homolytic cleavage. Okay, so let's look at that. And now we've generated two of these oxygen radicals. I'll just put a 2 down there. Okay, so we're still not quite ready to involve the alkene at this point. We can continue in the initiation, which is to generate bromine radicals from our oxygen radical. So we're going to react our oxygen radical with HBr, and we're basically going to do a hydrogen atom abstraction from HBr. Okay, so we're going to have that set of arrows. Okay, so this set of arrows right here, okay, what is that showing us? What bond are we forming when we are combining that radical with the hydrogen electron? So we're making a bond, right, between oxygen and hydrogen. So we've just made that alcohol, ends up being a byproduct, and we've generated the bromine radical. Okay, so you might be thinking, well, wait a minute. I learned a reaction, at the beginning of chapter 8, which was free radical halogenation, where we generated a bromine radical through homolytic bond cleavage of a Br2 molecule. So why is it that I need to go around this backwards way of generating the bromine radical in this case? Well, remember that Br2 reacts with alkenes through electrophilic addition, like we learned in chapter 6. And it turns out we can't shut down that reaction even in the presence of heat or light. And so we need a different way to generate the bromine radicals to shuttle us into this free radical addition mechanism. Okay, so now we're ready to go ahead and look at the propagation steps. Remember, the second step is propagation. Okay, so what are the two things that must happen in the propagation steps of all free radical chain mechanisms? So remember, one of them is to regenerate the propagating radical. So in this case, it will be bromine, the bromine radical. And then the second thing is we need to make our product. Okay, so let's consider how we're going to do this. So there's going to be two propagation steps here as well. Okay, so the first one is going to involve our alkene plus bromine radical. Okay, so we have two possibilities here, really. We could do a hydrogen atom abstraction, okay, but it turns out that the pi bond electrons are more available than the carbon-hydrogen sigma bond electrons. And so that bromine radical, it's easier for it to interact with the electrons of the pi bond. Okay, so let's go ahead and look at what the mechanistic arrows are. Okay, so that bromine radical is going to combine with one of the electrons from the pi bond, and then the other pi electron is going to generate a carbon radical. This is the key step that determines the regioselectivity. Okay, so let's see how that works. Okay, so we just added the bromine to that secondary position. Okay, so why did I add the bromine to the secondary position? Well, that was so that the radical would be at the more substituted position. So I'm still following the path of least resistance in terms of energy. And in this case, I'm putting the bromine at the less substituted position so that the radical ends up at the more substituted position. Consider what an alternative mechanism might be. Okay, so compare to this set of mechanistic arrows. Okay, so what if when the bromine radical combines, then we give that other pi electron to the less substituted position. Okay, so this would be giving us the minor product in terms of regioselectivity. Okay, so this would lead us to our minor product, which would be Markovnikov's product. Okay, so notice here we have a tertiary radical versus a secondary radical. The tertiary radical is more stable and is favored. Okay, and so since it's more stable, it will form faster, and that's going to lead us to our major product. So let's make a note here, leads to major product. Okay, the secondary radical, this could be, so this is less stable and would lead us to the minor product. Okay, so we're still following, the rules of energetics as we talked about, in that we're going to go through the most stable intermediate. But since we add the bromine in this first step and generate the radical at the same time as carbon-bromine bond formation, we need to put the bromine at the less substituted position so that the radical ends up at the more substituted position. And that's what determines the regioselectivity. Okay, so we're going to take that tertiary radical with the secondary halide that we've made, and we're going to continue our propagation steps. Okay, so we'll take our favored radical intermediate, again, tertiary was more stable than secondary, and we need to finish up making our product and regenerating our propagating radical. Okay, so we're going to take another molecule of HBr to do that. So we're going to have the carbon radical combine with one of the electrons from the HBr bond, which basically, again, is a hydrogen atom abstraction. And now we'll generate our product. Okay, so we have our secondary halide. Oops, my pen stopped working. All right, there we go. And we regenerated our bromine radical. Okay, so there's our overall product, and we've regenerated our propagating radical. Okay, so I want to just look at the stereochemistry for a second, okay? Because what you might have noticed up top, I showed the products of this step as racemic. I had that bromine coming in on a wedge and a dash. So let's just make a note that that was a chiral center, and here let's talk about the stereochemistry for a second. Okay, so remember, a lot of times that when we're considering stereochem, we need to think about what step in the reaction was it that I generated the chiral center. Okay, so relative to this chiral center that I've highlighted there, okay, we're generating that in the first step of the mechanism. Okay, so notice how this carbon was sp2 anhybridized, and it's going to an sp3 hybridized carbon. So it's this step in which I'm generating that chiral center. Okay, so since this carbon in the starting material is sp2 and planar, when that bromine radical comes in, it can come in from either face. And so we end up getting a racemic mixture at this point. Okay, so that bromine would have been on a wedge and a dash at that point. And then I want you to imagine, what if I was generating a chiral center at that more substituted position? Like, it's not in this case, but what if this carbon then went to a chiral center in the product? Okay, so remember that carbon radicals are sp2 hybridized in trigonal planar. So when the hydrogen adds to that carbon, it can do so from either face. We're not showing that in this product though, because this carbon doesn't end up being a chiral center. But one of the examples we'll look at in a few minutes does generate two chiral centers, and we'll see that there is no specified way that the hydrogen and the bromine are adding. The bromine can add from either face, the hydrogen adds from either face. It's not a stereospecific reaction. So if we're generating two chiral centers, we get all four stereoisomers. Okay, so those are the propagation steps. Lastly, we need to consider the third and final step of our free radical chain mechanism. Okay, so what is the third and final step? So that's termination. I'm just going to show one example of a termination step. So one example. And for my purposes, the easiest one to write out is the two bromine radicals coming together. So bromine radical and bromine radical. Remember, in the termination steps, we're basically destroying any leftover radicals from the reaction. Okay, so there's the one example, but again, you could choose any two radicals that you formed up above in your initiation or propagation steps and bring those together in termination. Okay, so now we've seen the mechanism, we've accounted for the regioselectivity, which is anti-Markovnikov. So I just want to look at one or two examples to highlight the stereochem and just remind ourselves of the issues we talked about in the reaction. Okay, so here's one example. So the first example I want to look at generates two chiral centers. We actually used this as a example when we were looking at, let's get rid of that. We've looked at this example, alkene, for lots of different reactions because it allows us to see various aspects of the regiochemistry and the stereochemistry. Okay, so the reagents are HBr, and then we have ditert butyl peroxide, DTBP, and we have heat. Okay, so what we need to think about first is the regiochemistry. So let's draw the product without stereochemistry. Okay, so let's look at these two carbons of the alkene, so carbon 1 and carbon 2. So which one of those carbons, carbon 1 or carbon 2, should have the bromine in the product? Okay, so carbon 2 is less substituted, and so it's the carbon that should have the halogen, and carbon 1 should get the hydrogen. So the products without stereochemistry have the halogen at the less substituted carbon, which we numbered carbon 2, and the hydrogen at carbon 1, the more substituted side. Okay, so carbon 1 and 2, are those newly formed chiral centers? Yeah, they are both chiral centers, right? So carbon 1 is a chiral center and carbon 2 is a chiral center. So we have two new chiral centers and 4 possible stereoisomers. Okay, so we mentioned when we were talking about the mechanism that the bromine can add to either face, the hydrogen can add to either face. This is not a stereospecific reaction, because the carbon-bromine bond and the carbon-hydrogen bond are formed at different steps of the mechanism. And so we'll observe all 4 possible stereoisomers. Okay, so the 4 stereoisomers that we will get, so let's make that note, observe all 4 stereoisomers. We could just make a note below, this is not stereospecific. Okay, and then we could draw them down below, here they are. Okay, so we could have all combination of the methyl group and the bromine being both wedges, we could have them both dashes. And then we could have the 2 trans options. So we'll put the methyl on a wedge and the bromine on a dash, and then the last trans option would be to alternate and put the methyl on a dash and the bromine on a wedge. Okay, so we would observe all 4 possible stereoisomers. There they are. We talked about how this is anti-Markovnikov in terms of its regioselectivity, and there would be the 4 products in a 1-to-1-to-1-to-1 mixture that you, in terms of the major product that you would observe. The minor product, again, would put the halogen at the more substituted side. Okay, so let's look at one last example of this reaction, and then we'll finish up this chapter by talking about allylic halide bromination. Okay, so the last example we're going to consider, let's look at this molecule. So ditert butyl peroxide and heat. Okay, so let's count our carbon chain. So we have a 5-carbon chain. Our alkenes between carbons 1 and 2. Okay, so in the product, which carbon should end up with the halogen? And then which carbon should end up with the hydrogen? Okay, so carbon 1 is less substituted, so it should end up with the halogen. There it is. And then carbon 2, neither of these are chiral centers, so we don't have to include any stereochemistry there. Okay, so I want you to look at this product for a second. Okay, so notice how we just made a primary halide. This primary halide ends up being super important for, we'll see this a lot of times, primary halides in general, and we get to chapter 9, we use them as starting materials for some reactions we're about to talk about. So what I want you to think about is what reaction have we utilized so far in this class that uses primary halides as one of its reagents? Okay, so what I want you to think about is, what did we use these for previously? So I'll give you a hint. So remember when we were making carbon-carbon bonds, the only way we knew was between an acetylide anion and typically a primary halide. Okay, so we said methyl and primary halides were the best in that case. You could sometimes get away with using secondary. And so in terms of synthesis, think about how you might incorporate this kind of reaction, okay, to make our primary halides that we could then couple with an acetylide anion to do carbon-carbon bond formation. Okay, so the next reaction that we're going to talk about is the last reaction of this chapter. It's similar to the others in that it's a free radical reaction and that it's a bromination reaction. Okay, so let's introduce this reaction. So our last reaction to talk about here is something called allylic bromination. Okay, and so before we actually look at the reaction, I just want to remind you guys of some terms that we've used, specifically allylic, and how that relates to the product and the intermediates that we're going to see in this reaction. Okay, so first let's just draw a molecule and indicate its allylic position. Okay, so remember that the carbon adjacent to a carbon-carbon double bond, so that one I've labeled there, that would be the allylic carbon. Okay, and then the 3 hydrogens that are attached, okay, these 3 hydrogens would be the allylic hydrogens. Okay, so what we're doing in this reaction is we are taking a molecule that has an allylic carbon-hydrogen bond, and we're substituting that for a bromine. So we are doing a type of free radical halogenation, but it specifically occurs at the allylic position. Okay, so the products that we get in this reaction are going to be allylic bromides. Okay, so the most simplest one would be this. So this would be an allylic bromide. And so this is the type of bromides that we're going to make in this reaction. Okay, and then the last thing that I want to remind you guys about is, what was significant about the allylic position in this chapter? Why have we talked about it recently? Okay, so we've talked about it recently because the allylic radical was stabilized through resonance. Okay, so remember that we could draw a resonance structure basically that shows, how that carbon that is electron deficient, the radical position, is delocalized through resonance, which was a stabilizing feature. Okay, so this was the allylic or the allyl radical. And we'll see this as an intermediate in this reaction. Okay, we aren't actually going to look at the entire mechanism of this reaction, but we will talk about some of the highlights of this. Okay, so how do we do allylic bromination? Okay, so the reaction, the allylic bromination conditions look like this. Okay, so generally, we'll take our molecule that has an alkene and has an allylic carbon-hydrogen bond that can be reacted, and we are going to react it with something called NBS. Okay, let me get that straighter. Okay, so NBS, and as it's a free radical reaction, we need heat or light, so delta or H nu. And what we're going to do in this reaction is we are going to generate an allylic halide. Okay, so we're going to do a substitution reaction where one of the allylic carbon-hydrogen bonds is substituted for a carbon-bromine bond. Okay, and so we end up having to use NBS, which is our source of bromine, because it carefully controls the amount of bromine that's available in solution. Okay, so you cannot use Br2 and light here to do allylic bromination. Okay, so let's just tell you what I mean here. So we learned of this reaction, Br2 and light, or heat, at the beginning of chapter 8, which was free radical bromination. Okay, so yes, you could get some of the allylic bromide, but you also get, as a byproduct, the electrophilic addition, or as, a set of products, you would get the allylic bromination product and the product that comes through electrophilic addition, which is what we learned in chapter 6. There's no way to shut down that electrophilic addition, okay? And so we use NBS, which allows us to kind of circumvent the problems of using Br2 in this reaction. Okay, so what is NBS? All right, so let's define that over here. So NBS is N-bromosuccinimide. So N-bromosuccinimide. All right, so what does that look like? So it's this structure. So that's N-bromosuccinimide. Okay, so that nitrogen-bromine bond, I don't have its specific BD here in my notes, but it's the bond that we can homolytically cleave in the presence of heat or light, and so it allows us to initiate the free radical reaction. And so one just, random nomenclature thing is, so where did that term come from? So N-bromo is pretty clear because we have a bromine attached to an N, a nitrogen. But where does that succinimide come? Okay, so succinimide comes from the word succinic acid. Okay, and succinic acid is this dicarboxylic acid. Okay, so this is succinic acid. Okay, so just to see where that comes from, this is the 4-carbon chain where I have carbonyls at position 1 and 4. So you'll learn about the reaction, the reaction that goes from succinic acid to succinimide when you get to organic too. So basically, how do you convert a carboxylic acid into an amide? So notice how both carbon 1 and carbon 4 were carboxylic acids in succinic acid, but in N-bromosuccinimide, they're both amides. Okay, so that was just like a random nomenclature thing that I wanted to, or common name thing that I wanted to bring up, where that term succinimide came from. Okay, so let's look at an example of this reaction. And for this example that I'm going to give you, we'll talk about some of the key mechanistic steps. And specifically what we're going to take a look at is the allylic radical and think about how that can help us determine what the major product of this reaction is. Okay, so here's our example. Okay, and we're going to build complexity into our examples because we'll see that there are some issues related to symmetry of the molecule and also the various allylic positions and their resonance structures that is going to determine the fate of this reaction in terms of the major product. Okay, so here we have NBS and we have, we'll just use heat in this case. Okay, so I want to go ahead and just count the carbon in the ring so that I can talk about the two, allylic positions. Okay, so which carbons there's two carbons, which two carbons in the cyclohexene are the allylic positions? Okay, so hopefully you said carbon 3 and carbon 6. The next thing I want to ask is, are they the same or are they different? Like in other words, could you distinguish them from one another? Okay, so hopefully you said that carbon 3 and carbon 6 are the same. They're related through symmetry. If you cut that molecule in half, with a horizontal plane of symmetry. Okay, so why I bring this up is because it doesn't actually matter which allylic position you choose in this case. Okay, so I'm arbitrarily going to put the halogen at carbon 6, but you could have done that at carbon 3 as well. And we'll see, because of the mechanistic intermediate ends up being an allylic radical, we end up with racemic mixtures. Okay, so the bromine could have come in on a wedge or on a dash, and that would be racemic. Okay, so we're not going to talk about this mechanism in detail. If you want to look at it, it's in our textbook in full. If you wanted to just see, kind of how the various propagation steps worked out to form the major product. But what I do want to talk about is the key mechanistic intermediate and how we have to consider its structure. Key mechanistic intermediate. Okay, so it is the allylic radical. All right, so for this reaction, what I want you to consider, well, what would be the allylic radical? So it would be that allylic radical, okay, to give me the bromine at carbon 6. Okay, and if I put the allylic radical at carbon 3, it would be the same structure, just flipped over. Okay, so the other thing I want to consider is in this reaction, what are the allylic radical resonance structures look like? Okay, so we could draw those curved arrows, and we would get to this structure. Okay, so what I want you to rationalize is, would those two allylic resonance structures, allylic radical resonance structures, would they give us the same product or would they give us different products? Okay, so they would give us the same product, right? So, however you might need to flip the molecule over or rotate it to get it to match what we have up above, but both of those allylic radical resonance structures are equivalent in terms of what product they would give us. Okay, so what would happen if I had two different allylic radical resonance structures? How would I decide which resonance structure to use going forward in the product? Okay, so that's what we're going to look at next. We're going to look at an example of, well, let's generate the allylic radical, consider the resonance structures, we'll see they're different, and we'll try to think about what factors are controlling formation of the major product. Okay, so let's go ahead and do that. So the example we're going to look at here is going to be 2-butene, and we're going to react that with NBS. Okay, so let's go ahead and look at, first let's count our carbons so that we can track them. Okay, so the first thing to consider is, well, where are the allylic positions? So there's two allylic positions, carbon 1 and carbon 4, but they're also related through symmetry, so we only need to consider one of them. Okay, so we actually have, let's consider then the allylic radical at carbon 1 and its resonance structure, and then think about if those two allylic radical resonance structures would give us the same product or not. Okay, so the first thing we're going to do is we're just going to consider the allylic radical that is initially formed. Okay, so that would be this structure. Okay, and then let's consider the resonance structure. Okay, so remember we basically transposed the position of the alkene and the radical. So we get to this structure. Okay, so look at these two. Are they the same or are they different? Would they give us the same product or a different product? Okay, so we're thinking about basically, wherever the radical is, that's where the halogen is going to end up. In this case, it's bromide. Okay, and so let's just draw what those two products would be. Okay, and we'll label them. Okay, so we'll make this A and we'll make this B. Okay, so first, what is the product for A? Okay, so it would be this primary bromide. So this is from A. And then B, this would be from B, and that is a chiral center there. So you would have a racemic mixture of, wedge and dash there. Okay, so which one of these is the major product and which one is the minor product, and how would we determine that? Okay, well, of course, we're gonna have to go back to the allylic resonance structures and consider, what's the difference between them? Okay, so you might look at them and say, oh, well, let's see. Structure B has a secondary radical, so maybe that's gonna be the major product. Okay, but we're then completely ignoring another factor that is contributing to the stability of these molecules. Okay, so let me work through this with you. Okay, so in molecule A, so that radical, what is the substitution of the radical? Okay, so we have a primary radical. Okay, so what is the substitution in B? Well, it's a secondary radical. Okay, so what else is different about these two structures, A and B? Okay, so yes, they have different substitutions of the radical carbon, but notice that the alkene also has differing substitutions. And we learned that alkene substitution patterns determine alkene stability, okay? And the alkene stability also contributes to the overall stability of these molecules, right? It's not just like the radical stability in isolation. There's different factors controlling to the overall stability of these structures. Okay, so both the radical stability and the alkene stability we have to consider. Okay, so then what is the substitution pattern of the alkene in A? Okay, so we would call this a disubstituted alkene, right? Because there's two carbons bound to the, to the alkene carbons. So this is a disubstituted alkene. Okay, and then what about for B? So B is a monosubstituted alkene. Okay, so a monosubstituted alkene. All right, so the radical stability and the alkene stability are going against one another, right? Because in A, I have the less substituted radical, but the more substituted alkene. And in B, I have the more substituted radical, but the less substituted alkene. Okay, so if one of those factors, either radical stability or alkene stability or substitution, if one of those is more important, that would give us, either A or B is the major product. Okay, so what if I told you that product A is the major product and B is the minor product? Okay, so what would that tell you? Which factor is more important? The substitution of the radical or the substitution of the alkene? Right? It's the substitution of the alkene that ends up being more important. So what we can infer from that is that the substitution of the alkene dictates the overall, allylic radical resonance structure stability more than the substitution of the, the carbon that bears the radical. Okay, so the resonance contributor of the allylic radical with the more substituted double bond is what's going to dominate and lead to the major product. Okay, so let's make that note. Okay, so allylic resonance structure with more substituted double bond, substituted alkene, we'll say, dominates and leads to the major product. Okay, so in the two examples we've looked at now, so in the first one when we had just cyclohexene up top here, up here, our two allylic radical resonance structures were equivalent. They both had a disubstituted alkene and a secondary carbon, right? They were the same things, just flipped over. In our next example now, we had these two allylic positions 1 and 4, but they were equivalent. So we looked at, just arbitrarily putting the allylic radical at carbon 1, and then we considered the resonance structures. Here we had two different allylic radical resonance structures, and we, went through, which resonance structure would give us which products, and we came to the conclusion that alkene substitution was more important. So our last example is going to basically put in one more layer of complexity, which is in the beginning, what if carbon 1 and carbon 4 were not equivalent? Like, what if I had two allylic positions that were different from one another? Then what would I consider? Okay, so here's our last example for this reaction. Okay, and in through this example, we can also talk about stereochemistry. Okay, so this is the starting material we're going to use, and we'll do NBS and heat. Okay, so again, let's first count our carbons so that we can talk about them. Okay, so which carbons are my allylic position? Okay, so hopefully you said carbon 5 and carbon 3. Okay, are they the same or are they different? Are they distinguishable from one another? They are, right? So carbon 3 has a methyl group and carbon 5 does not. So carbon 3 and carbon 5 are different allylic positions. So how would I know where to initially form the allylic radical? Okay, so here now we're going to consider between the two allylic positions, carbon 3 and carbon 5, which one would form a more stable initial radical? Like if I put the radical at position 3 versus position 5, which one would be more stable? Okay, well, hopefully you can see that at position 3, we would have a tertiary carbon radical, whereas at position 5, we'd have a secondary carbon radical. Okay, so what we're going to do is first consider this allylic position that gives us initially the more stable radical. So in this case, it's tertiary versus at carbon 5, it would have been secondary. Now I can go ahead and go through the procedure of considering the allylic radical resonance structures, okay, just like we did in the previous example. Okay, so here's my two allylic radical resonance structures. So let me put my numbers on here in case you having trouble seeing how I got these various structures. Okay, so here I have my initially formed tertiary carbon radical, and then I considered the resonance structures and I got to the radical at carbon 1, which is secondary. Okay, so now we can go ahead and look for the more substituted alkene. Okay, so which one of these two allylic radical resonance structures has a more substituted alkene? Okay, so what's the substitution pattern on this one on the left? Okay, so the alkene is disubstituted. So this is a disub alkene. And then what's the substitution pattern on this one on the right? Well, it's a trisubstituted alkene, right? Because it has, let me just point them out, it has this carbon, and that carbon bound to the carbons of the alkene, right? So it would be trisubstituted, whereas up here I only have carbon 3 and carbon 5 bound to the two carbons of the alkene, so it'd be disubstituted. Okay, so we just talked about how the more substituted alkene will lead to the major product. Okay, so since it's more sub, it's going to lead to major product. Leads to major product. All right, let's go ahead and draw that. Okay, so when I add the radical at that position 1, we'll be generating a chiral center, and since when the bromine is going to interact with that carbon radical that is trigonal planar and sp2 hybridized, it can do so from either face, and so we would end up with a racemic mixture here. So the bromine could come in on a wedge, or the bromine could come in on a dash, and that will give us our racemic mixture. Okay, so the last thing that I want to do now is consider the various ways that we can make or various halogenation reactions that we could consider. So I'm going to try to work through these in my head as we're, as I'm going through this. Okay, so let's start back at the beginning. Okay, so I want to consider bromination reactions. Okay, and as it relates to lecture, I'm just going to go ahead and write them out. And I want you to try to predict the products of them and consider their various components. And then I will add the structures when I upload the notes so that you can check your work. Okay, so the first one that we have would be an alkene and HBr. The next one we have would be an alkene and Br2 in an inert solvent. We also could take an alkene and react it with Br2 in a non-inert solvent like water. Okay, so those I think cover all the chapter 6 halogenation reactions. You could also consider the chapter 7 alkyne halogenation reactions, but they're unique because we reacted those two pi bonds. We ended up with, either a dihalide with the case of HBr2 equivalents or a tetrahalide in the case of Br2 equivalents. So I'm going to ignore those for now. Okay, and now we have some new ones to add in, right? Okay, so the first one we learned in this chapter was Br2 and heater light. Okay, so that was free radical halogenation of an alkane. Next, we learned HBr and peroxides. So ditert butyl peroxide and heater light. And then lastly, to try to get this all on one page, we just learned about allylic bromination. And I actually need to change the starting material to be able to do allylic bromination in this case. So I'm going to make it that. And the reason why that is because if you took that alkene that I had used in all the other starting materials, you would end up with multiple potential initial radicals and you would just get a whole mess of different products there. Okay, so NBS and heat. Okay, so what I want you to do is spend some time thinking about each one of these reactions in terms of what's the mechanistic intermediate, what's the regiochem, what's the stereochem, and what's the different end products. A lot of them have Br2, some of them have HBr. In the end, they all are going to end up at least with one and maybe two bromines in the products, and don't want you to go ahead and predict the product. So what I'll do is I will upload, when I upload the notes, I will have the answers to these predict the product questions so you can check your work. Okay, in the second part of lecture today, I'm going to go ahead and start chapter 9. So just some of the introductory concepts in chapter 9 is what I'll do next in part 2. Okay, see you guys in a little bit.